că ăsta are un pic de lag. Stau record. Oh, of course you're doing setup now. Fingers crossed. Ok, n-are un pic de lag, are mai puțin lag. Cool, we're live. I'm gonna also record this to the cloud. Cool. So let's welcome Vasily. He will tell us about how we can design a nice looking modular monolith. Since modular monolith is a super hype keyword right now. So by the end of the talk, you'll know how to design one of these. Ask your questions either in YouTube, whether in Zoom if you're with us in here. But by the end of our presentation, you'll be able to unmute yourself so you can ask the questions live, only if you are on Zoom with us. So, Vasily, the stage is yours.
Alrighty, so designing a modular monolith is the topic of today. So, as I said, my name is Vasily Lenik. I'm a senior developer and the owner of a humble YouTube tech channel where I cover topics around .NET and architecture and detailed design. Also, quite recently, I found myself a nice hobby that's finally not programming or gaming related, which is driving slow cars really fast, within the legal limits, of course. But hey, sorry about all the car references throughout the whole presentation. There are going to be a bunch. Now, the whole presentation is going to be structured around 4 things. And let me just move this thing out of the way. Yeah, so the plan for today is to go over about 20 diagrams or schemas. We are also going to talk about food. And this is my cue right here because it's 6:30 and I'm standing between you and a well-deserved evening rest after a hard day at work. So it's going to be a tough situation to find myself into. And I'm going to joke a little bit more than usual over here. Also, we're going to obviously discuss about architecture and define what a boring architecture should look like. And the cherry on top, we're going to go over how you can set up a more effective communication within your team. The whole presentation itself is going to be split up into 3 different sections. The first, the most boring one, which is the reasoning behind using a modular monolith. Then we're going to go over the technical aspects like basic solution structure, defining module boundaries, defining communication patterns, and how modules communicate with each other, data isolation practices, and all that stuff. And finally, my third session, and the one I prefer most, is challenges when it comes to working with modular monoliths, like challenges working with people, migration from a monolith to a modular monolith, and then to a microservices-based system, issues that might appear during or after the migration, resiliency patterns for resilient communication with external components, testing practices, of course, and how you can enforce your design decisions. Now, next, and the first slide for the day is going to be the non-functional requirements. So there are a bunch over here. And personally, I think that non-functional requirements are the things that bring in most of the fun to any kind of architectural or design challenge. Now, you can have 2 functionally identical systems, let's say 2 cars, and the core use case of a car is getting you from point A to point B. But God, would I love to get from point A to point B in a BMW or Mercedes rather than in a Dacia or a Nissan. And yeah, I don't discriminate against your opinions on cars or your preferences. I'm stating that I really love European-based cars. Now, Q&A session, as Irina mentioned, is going to be at the end. I tried in the past running the Q&As during the presentation itself. It didn't work out, so bummer, you will have to write down your questions either in YouTube or write them down on a paper. And by this moment, you've already read the description over there, so the light bulb on a circular thingy, on a blue circular thingy in the background is going to be a noise trigger, which means we are going over a debatable topic just like this one. So the first topic of our day is what exactly is a model? And by the way, the whole presentation is highly opinionated on my personal experience with how I was building modular monoliths in the past. So the definition of a model is quite simple. It's encapsulated data and behavior that brings some form of business value. Now, the fun fact is that we can apply the same definition to a single microservice, since essentially a microservice is encapsulated data and behavior behind a well-defined API, let's say REST API, GraphQL API, gRPC API on top, which brings some form of business value. And I don't plan to jump into the rabbit hole, which is called the monolith versus microservices debate that's raging all over the internet for a couple of years already. I'm just going to state my opinion on the matter, which came after, well, a couple of years of experience in there, is that hosting topology is not really architecture. Hosting topology is part of the architectural scope, and it is a decision that has to be made and that has a big impact on the overall structure of your system. Now, why the hell do we have that debate in the first place, and is it really worth it to look at it? The answer to that is it depends, but overall it's worth it to read through all the comments and all the blog posts online. I think all the technical YouTubers or bloggers have already covered that topic one way or the other. But the idea here is the fact that we can view a system in through more than one lens. So most of the topics online cover it only from the physical perspective, but there are at least 3 more. For the purpose of this presentation, we really care about only those 3. So there can be a logical view, development, physical, and process view. And also the scenarios in the middle are use cases. But when we go through a physical lens and view a monolith and a microservice, they are drastically different. The most basic example is a monolith has only a single repository. Quite simple or straightforward CI/CD pipeline. You have only one artifact or deployable unit that you get in the end. And you have a team of developers that might be bored with their repetitive work, but are overall kind of happy with how they are working right now. On the other hand, you have the fun part, the microservices, where you have tons of repositories, even more CI/CD pipelines, a lot of artifacts flying around all over the place. You have developers that might be fanatically searching through logs to find the cause of some issue that spans across multiple microservices, and a couple of operation guys crying somewhere in the corner since they were against the idea to deploy on Friday evenings in the first place. Yeah, I'm joking about the microservices side. It's not always that bad in here. We do tend to have good times also. But you get the overall point of view over here that a monolith quite drastically differs from a microservice if you look at it from the physical perspective. Now, we're talking about modular monoliths here. And modular monolith is also still a monolith, since you deploy it as a single unit. Now, if we take a look at a modular monolith and a microservices-oriented system, from the logical perspective, the difference is quite stark also, but it's not that bad. Let me just next. Okay, so yeah, from a logical perspective, a monolith and a microservice environment do not differ that much. And sorry for the obscure diagram, which was reduced to only a bunch of boxes and lines over here. That was done for a reason. So on the left side, we have a monolith, which covers functionalities A, B, C, and D. We don't care about those exact functionalities. We only care that they are there. And on the right side, we have a set of microservices that cover the exactly same functionalities, A, B, C, and D. However, they are deployed as a set of microservices. Now, why the hell did a team decide to stick up with monoliths, and the other team decided to go with microservices to solve the same functional problem? The answer to that lies in the non-functional requirements that we covered, well, that we went through at the beginning of the presentation. Things like, I don't know, number of users that you need to serve, the cadence of the releases for each of those components, availability requirements for all of those components, even the number of the teams that are working on a certain project are going to impact your decision one way or the other. And you're obviously not going to have the answers to all of those questions from the get-go. And you might not even during the development phase not get answers to all of your questions. So if we take, for example, a greenfield project or startup, and startups are born in a relatively high volatility environment, where an architect at a startup might be asked to design against a potential set of incomplete functionalities or functional requirements, and even more hidden constraints that are there, but he has to exercise some discovery mechanisms or discovery meetings just to figure out those unknown constraints. And I mentioned microservices, I mentioned startups. So it's obviously, we're going to mention the mantra that's all over the internet right now, that you should not start with microservices, but rather with a well-structured modular monolith with with well-defined logical boundaries inside it. And I think 10 minutes into the presentation, we should define what a modular monolith really is. A modular monolith is basically a software architecture approach where you maintain a single cohesive code base, and inside it, the application is divided into logically separated, loosely coupled modules that each cover a set of respective functionalities. Now, why should we start with a well-defined modular monolith in the first place, since you're going to invest into the upfront design for that system nonetheless? You could start off with a traditional monolith, tightly coupled, and end up with a big mess of code in there. But you can invest into a modular monolith at the start and get the following benefits. So first of all, it's easier to start with a monolith than it is with a set of microservices, and easier to get going and to validate some initial ideas. Then you're not going to incur the cost of running microservices, which is the operational overhead that you have with microservices when running a single monolith. And finally, you will win enough time to flesh out the unknown constraints that I mentioned previously, since the constraints will be there, and it will be an exercise in discovery for you to find them. And at the pivotal point where you will have to decide to either go the microservices route or still remain with a monolith, you're going to have a better image and more information to base your decision upon. Now, building modular monoliths is not easy, and Simon Brown over here has a really nice phrase that if people can build monoliths, microservices won't help. So we should figure out how we can build modular monoliths properly. But before that, I have a question for all of you to think about if you have a favorite car that you would like to buy in the future, because I certainly do. But with the current circumstances and current market, I can only afford something like this, which is a Lego toy. And I'm bringing Lego to software presentation, which is really risky here, since Lego and software are seemingly two different topics over here, and they might not have much in common. By the way, if you've never built a Lego, I don't know under which kind of rock you're living, but go ahead and buy your favorite toy, I don't know, Harry Potter or toys or like that, and build a Lego. It's really awesome. But for our purpose, we should know that a Lego comes with an instruction and with a set of building blocks that when we assemble together, we get some components. Based on those components, we can then assemble and integrate those components together to get the final toy. Now, the bummer is that when we build Lego, we usually build it alone. But when we work on software, we collaborate with our team, and we need to communicate and interact with team members. Introverts, I'm sorry for that, that's how life works. So it's bad enough when two people are referencing the same element, but using two different terms. But it's even worse when they are speaking about two different things using the same term. I learned that the hard way. So at some point in the past, we decided as a team to find a glossary of terms that we are gonna use. And the C4 model was nearly perfect for our code. If you've never interacted with C4, it's basically a way for software teams to describe and discuss about architecture and code base. It's basically a set of glossaries, a set of terms that are used in certain ways. So C4 has 4 different contexts at which we can introduce diagrams: system, containers, component, and code element context. When we talk about system, it's basically the thing that we are building or any kind of other system that we are interacting with. A container is a runnable thing that we need in order for our entire system to work. So traditionally, the containers in a simple application might be a client application container, a web API that serves that client application, and a database. So those 3 are different containers. And when I mean container, I don't mean Docker container. I only mean container as in C4. Now, every container is built out of certain components or a set of components. And if you take a look at the diagrams that are on c4model.com, I believe the original site is, you can see that the author is using things like controllers, services, facades, proxies as components. For the purpose of a modular monolith, that's way too atomic. And we agreed with the team to use the term component with a model. So it's not the original and the real C4 glossary. We're using the component as a set of code elements. So obviously, if we want to go to the level of controllers, facades, proxies, and all that stuff, all of that are code level elements. But the model itself, the abstract set of code elements, is called a component. So in the whole presentation, I'm going to use the term component and model. I might interchangeably use them, but if I say either one of those terms, know that I'm referring to the same thing. The issue with 2 terms and a single thing all over again. So the next slide is all about solution structure. And this is a template that I prefer using for modular monoliths. I'm coming from a .NET world right now, so I'm not sure if the terms apply for Java or Python or something like that. But in .NET, we have the term class libraries. And class libraries are basically a bunch of code, a bunch of classes that are built up together and served as a single package. So essentially, the rectangles, the colored rectangles, are class libraries. The dashed borders are the logical boundaries of a single component. Since a model or a component, as I said, can have more than one class library or more than one code element. The default structure that we were adhering to was the fact that the host itself is a component that is responsible for DI setup, settings, and all that related functionality. Then each model, let's take model A, for example, right there, has a routing class library where if we are building a web API, and let's suppose we're building a REST-based web API, since those are the most popular ones, in the routing class library, we're going to have the code that's responsible for API controllers, like API endpoints, controllers, minimal APIs, I don't know what other fast endpoints and all that stuff that has appeared over the years. So the way we expose functionality to the external world goes into the routing. Over here, if you're using GraphQL, might go your mutations or your queries. The next and the most important part of any model is the contracts class library. And the contracts class library will basically maintain all the abstractions for the business layer logic. What I mean by that is if you're coming from, let's say, anterior structure, when you have the client layer, business layer, data layer. Well, the contracts are the abstractions of the business layer logic. If you're coming, for example, from a clean architecture or onion architecture styles and all those variations, the contracts are basically the application layer, not the domain, the application layer abstractions that the controllers are calling into. If you're coming from a CQRS setup, basically the contracts are the commands, queries, and events that a model produces. By the way, events are also part of contracts. And next, finally, is the implementation details class library, which can be one or more class libraries. I prefer having only one and having a well-defined folder structure inside, like you have in model A, where you have a domain, application, and infrastructure. By the way, the implementation details are left for you to decide upon the difficulty, the how complex the model is. It's all up to you to decide. That's the fine part. As I said, the most important for me are the contracts for business layer logic. Next, the last component is utilities, which is all about cross-cutting concerns like logging, messaging, parsers, and all that stuff. Now, over here, we have model A and model B. We might have model C, D, E, F, G, and however many you want there. The question is, how do you define the boundaries of a model? And when do you know that you should stop and probably rethink your models, your boundaries? And the question is really debatable. And the original answer to all software questions that are debatable is it depends, since you will have to balance coupling and integration complexity. To explain that in a bit, I'll have to throw in some numbers. So let's say you have a system with 1, 10, 20, 50, or 100 different components. If you have 100 different small components, the integration complexity will slowly kill you, since integrating 100 elements into a single workflow, good luck with that. If you have a single component, on the other hand, the coupling, the tight coupling of all the stuff that goes into that component will also make it hard and less maintainable in the long run, and even more hard when you have to decompose that single big pile of mud into multiple smaller piles of mud. The way we define boundaries of a model is really not that straightforward also, since we have more than one way to do that in software engineering right now. We can have functional decomposition of our models. We can have, which is a thing to be avoiding at all cost if you have at least some amount of complexity inside your code base, inside your component. Since functional decomposition will result into multiple functional components, and when the functions change, your design will change with them. Domain-driven design comes with the term of bounded context, which is a really good candidate, since you will be splitting up your solution into areas of functionality. And also there is the third option, which is volatility-based decomposition. And volatility stands for things that change together, live together. And I prefer using a mix of the bounded context and volatility-based decomposition for when I do the decomposition of a system. Now, a rule I follow and which might help you out a lot is the fact that in the end, you should end up with a minimum number of highly cohesive, while still loosely coupled models, each generating value on their own, and when they are integrated together, they would solve a core use case set before a system. And an example of a real-world system would look like something like this, where we have a simple restaurant. It's the talk about food that I mentioned previously. So we have about 10 models in here, a listing of products, management, order management, payments, notifications, stocks management, administration, reporting, and all that stuff. If you're working for a, let's say, startup, since we started with startups, for a small company that's only growing up, you might not need to build all those models from the get-go. Your system might evolve as well as the business. And at the start, if you remember any kind of restaurants in the past, they were offering a paper menu. Well, hell, some of them do until this moment also offer a paper menu. Then it evolves at some point that a QR code sticks to the table, which you can scan, and then you get redirected to a static web page that might be served via some CDN. Recently, or the last couple of years, restaurants started creating web applications where you can order some food, then go through some payment process where you can pay by card, pay, for example, by cash with the courier and all that stuff. Notifications also evolved in time. So previously we had SMS notifications, emails. Now we might have application notifications. We might have an order tracking page where we enter the order ID, and then we can track all the updates in there. Kitchen ordering, order tracking has also evolved. If you've seen SpongeBob in my childhood, it has been a popular TV series. they had sticky notes that they were handing over to the chef to prepare food. So those sticky notes evolved into displays into our food court where we can interactively see where our order is. Now, that much is clear. So essentially you have more models. Each can evolve independently or together with some other models, since evolution works like that. But the question is, how big should a model really be? And we're going to take a look at the stocks management model over there to see the fact that it responds about two business functionalities. So the first one is monitoring existing stock to know when you are running out of stocks to produce food. And then it might be also responsible for procurement of new stocks or issuing procurements. Now, if you have a big enough model that you can split inside into several fine-grained services, and what I mean by fine-grained is basically coarse-grained is your general model, and then inside you have vertical slices, which each are responsible for some fine-grained functionality. That's really amazing. Personally, if I have such a model where I have a couple of functionalities inside that I can split vertically, I don't tend to create new class libraries for all of those components, for all of those fine-grained services, since I've seen in the past solutions with a couple hundred class libraries, and it was a nightmare to maintain. But if you have vertical slices inside a coarse-grained model, that's amazing, and you're doing a really fine job, and maintainability-wise and from navigation perspective throughout the whole solution, that's an amazing job for maintainability in the long run. Now, the procurement slice or the procurement service should also speak or chat to with the monitoring service to know when the stock is running out, or get notified somehow from the monitoring service that we are running low on some form of stock. So this is the part with the technical aspect with communication types. And for now, we're going to talk only about synchronous and, well, asynchronous communication, but only in the context of a single container, and all the models are inside that one container. So we're not going to the distributed right now. So communication types between different components of your system, different models, can be two: synchronous communication via the publicly defined interface in the contracts class library, or asynchronous communication via some form of message broker. Synchronous communication comes with the benefit that it's really easy to implement, it has no indirection, it's easy to maintain since you can see in the IDE all the places that you reference this or that method. It's also really fast. In-memory calls are blazingly fast compared to network calls or going over the wire. Now, the downside of synchronous calls is the fact that you are coupling your models. Well, it's not tight coupling since you're coupling only at the level of the contract, but model A will still depend on the availability of model B to process out the request. Now, on the other hand, you have asynchronous communication, which goes over a message broker. Asynchronous communication kind of fixes the issue with availability and coupling, since you will only be coupled to a message broker, so loosely coupled models, and high availability. Model B does not need to be active right now to process a message from a message broker. However, that comes with a cost of increased complexity. You will have stuff like duplicated messages, message loss, dead letter queues, message size, all those things. You'll have to take those into account. Also, if you're introducing asynchronous communication, you should think about eventual data consistency, since you're introducing eventual data consistency into your system and how you're going to tackle that. And finally, you have one more fail point for your entire system. So if the message broker goes down, good luck with the communication between models. So which one should you prefer? I would say neither nor, since both of them have their places. I prefer using synchronous calls within the boundaries of a single model, or within the boundaries of a couple of models if those are really tightly related functionality-wise, or if I need to query for some data. Otherwise, if I need to inform some other component, some other model about an event that happened in model A, I'm going to use message broker. This all also goes into the idea and the topic of Saga or orchestration, and we're not going to go in depth into that one, but we'll cover it in a little bit. So the next thing that we should care about is data isolation of each model. So each one of those should encapsulate its own data, since coupling at the level of the database is the worst thing that you can do. Because eventually, if you go with modular monoliths, you will probably want to decouple some of your models into external containers, into external microservices, let's say. And if you have coupling at the level of the data, that's going to be a pain in the ass to manage. Now, if you're coming from .NET, you might use SQL entity framework and define different DB contexts for all of the models themselves. But essentially, you're going to achieve data isolation through schemas. So each model will have its own schema where it has its own tables and the data. So each model will have its own schema. The next step, the evolution step in that aspect can be you can have different databases for each of your models, which is tricky from the cost perspective, since maintaining a single database with lots of different schemas is way easier than maintaining 4, 5, 6, 7 different databases for different models. And the final approach to data isolation might be the fact that not all of your models might need a SQL database in the backend. Some models might prefer to have MongoDB or JSON collection store. Some models might use even a cache better for their information. Or, for example, over here, model D is calling an external API to get its data from. All of those are really approaches to data isolation, but if you have to take one thing out, is the fact that each model should own its own data and encapsulate it as much as possible. My favorite part, challenges. Never heard of them. I wish I told you that. And the first challenge that we are going to cover is going to be people. And people is the biggest challenge, my personal biggest challenge, whenever it comes to software development. A person I really learned a lot from, one set of catchy phrase that stuck up with me, that people are usually the problem. However, people are also the solution. And that's really deep if you think about it. Now, what challenges you might have when working with people? First of all is the communication aspect that we've covered before. So two team members might be speaking about the same thing in different terms, or use two different terms to describe the same thing. Next, you have to manage their work, and planning is everything when it comes to team management and modular monoliths, since you are working on the same code base and can run into collisions or conflicts if your work intersects somewhere. So you'll have to define boundaries for the teams to operate. So, for example, a team might be responsible for a couple of models, the other team might be responsible for some other models, and they will have to interact with each other also when work is done across all of those when you have integrations across respective models. Now, in Army, there is a phrase that the speed of the entire column is equal to the speed of the slowest person. And that is especially true with modular monoliths, since you will release the whole thing together. It's not microservices where each team can have its own cadence of releases. You're going to release the same thing together, so you should plan accordingly. If a team is lagging behind, maybe you should look into feature management or something like that, feature flagging, or planning for the release in the future to be a little bit more aligned with your releases. Because at the end of the sprint, if a team has not managed to finish up all of their job, it's going to bring down all other teams because you are still releasing a single monolith. Now, the maximum number of teams inside such a system, from my experience, when you get to 3 or 4 teams working at such a system, that's the maximum amount, since you will have already thought about migrating to or decomposing your system into multiple microservices by that time, but for teams is the top that I've personally been comfortable with working. Now, earlier I mentioned the fact that we should be thinking about decomposing our system at some point in time, since we're introducing a lot of overhead into the upfront design. And the migration to microservices setup or to distributed is also an adventure that you should take with caution, because traditionally you can evolve based on the arrows you have on the screen. So a monolith can either go the distributed monolith way, which is something you should avoid at all costs, or you can go to a modular monolith or to a microservices. There are exceptions to the rules where you can evolve from a monolith to a set of microservices, to a set of well-established microservices, but those are more exceptions, since you'll need a capable team, you'll have to have clear functional requirements, you'll have to clear up all your non-functional requirements, all your boundaries, all your contracts before going into the microservices. So usually teams plan to go to a modular monolith setup where they have still the logical definition, logical boundaries of microservices, but still deploy a single thing in there. Now, traditionally, if you go through the process itself, it's going to look something like this. So you have the client, logic, and data layers. Then you split them up, introduce logical boundaries within it, and finally you introduce physical boundaries between your vertical slices. And now, let me admit some person in the room. Sorry. And the question is here, what happens to the data? Since this is all about code base and we're not talking about the data. What's the approach when you migrate data? Do you migrate first of all the code and then deal with the data, or do you migrate the data out of the database and then you move the code? I would say that you should strive to always migrate or decouple data the first, since if you try to decouple the code and then you understand that your data is still coupled, you will have to revert all your done work and you will have wasted a lot of effort. Since you can move first the data to a logical schema, as I mentioned previously with data isolation, the code will usually follow that approach. So once you have decoupled your data into a separate schema, you can decouple all your code base and then move to a separate microservice. And it would be great if you didn't break the whole system together during that migration. So patterns like Strangler and Fig will significantly improve your chances at success. Now, let's assume that you have decoupled your model into a separate microservice. What's next? There is obviously going to be some times when this model will have to work with a monolith to extract some data from other models. In those cases, you will have to introduce some proxy in there. So model A, B, C, and D can call model D through that proxy, and model D can call back the monolith through the public API that's exposed in the routing. But once you have all that established, there is a small problem that you might encounter, which is called, Houston, we have a problem. The external service is unreachable. And we didn't have that when we worked within a single modular monolith, since all the calls were in process. But now, for some reason, model A cannot call model C over the wire. And for demonstration, let's suppose we have a store or a web store or ticketing system. First of all, a store example. You have the orders model, which is model A. You have a payment gateway, which is model B. And then you have a stocks service, which is model C. Now, for some reason, you cannot call model C to verify the available stocks you have for a specific product. There is a business question. Do you block your users from ordering that specific product, or do you allow them to order it further? Now, if you decide to stop the money flow, and that means you decide to stop users from ordering that product, the business people are going to kill you, quite literally, since they are entirely dependent on the orders coming in. And the standard solution to this kind of scenario in the industry is called back ordering, where you allow users, customers to order the product. But then if you run into the situation that you no longer have that product, you just send an email with some sorry excuse, like say, well, we don't have that order right now. Here we have some loyalty points, and we'll deliver that order as soon as possible when it comes back on stock. The same example can be taken for a ticketing system. The same setup. Orders is A, payment gateway is B, and C is a ticketing system which offers you the count of tickets for a specific concert and how many there are left. So you cannot reach out the ticketing system. What are you gonna do? Business in these cases is gonna prioritize consistency over availability. So the first case was prioritizing availability of your business flows. Now it's prioritizing consistency. Since buying a ticket to a concert, then buying a flight ticket only to learn later that your concert ticket was canceled is quite the bummer. I was there and it's not pleasant, and it's really unpleasant situation to find yourself into and might result in some legal problems. Now, there are cases where the payment gateway might go wrong. So, for example, you have the orders, you have the stocks, but for example, the payment gateway goes out during Black Friday or something like that. There is sometimes not even an issue with that, since you can process payments at a later date or a later time. That's what happened to me last Black Friday. So you will have to figure out with the business, since this is not really a technical problem, it's more like a business problem together with some technical aspects. So you'll have to talk with business to figure those things out. Now, there is a thing. Was Model C really out cold, or we had some networking issues there? And to answer that, you'll have to implement monitoring on top of your components. And monitoring is about examining proactively the state of your system, so you get notified whenever something goes wrong, and you can take corrective measures as soon as possible to be back to business as usual. Every component in a system should expose a set of health checks, so the host in a modular monolith could pick them up and expose at some health URI, so the watchdog or your observability, or your monitoring setup could query those endpoints and see the state of your models or the state of your components. There are two places where you can place the health checks. One is at the level of the component, and one is at the level of the host. I prefer storing them at the level of the component, since when I will be migrating or decoupling the code base, I'll take the health checks together with me. But that results into cases where you have some redundant checks. Let's say A and B are checking against the same database. I'm fine with that, with those redundant checks, as long as I don't spill internal details to the host. So having all the health checks at the host level is going to be really tricky, since you need to know the internal details of all of your models. So it's basically a decision for you. I prefer having them at the level of each component. And now back to the topic of communication. What if really service B or service C was down? We have to deal with 7 rings of hell whenever we talk about calls over the network, and not even deal with the devil himself will help you out there. Because for external communications, for synchronous external communications, you will have to implement some retry mechanisms or some resiliency mechanisms. In .NET, we have Poly that comes with built-in retries, circuit breakers, bulkheads, and all that stuff built in, so you can create retry policies for synchronous calls. But all those fancy patterns aside, it's still a business-related issue, because calling twice on a non-idempotent API that was maybe late to respond to you, but still finish up the first thing. So for example, charging the customer twice for the same product because the payment gateway didn't respond on time is a quite tricky situation to find yourself into. Or trying to send repeated API calls or requests to a component that's already drowning is not going to make your situation any better. Now, there is also asynchronous communication that we should think about, and asynchronous communication comes with its own issues. For example, I mentioned previously eventual consistency, message bus being unavailable, message loss, message duplication, message versioning. Although in a modular monolith, you're not going to have that issue that much because you're still going to reference the same classes all over the place. And if you change the property the property name in one of those classes, you will either one, not be able to build the whole thing, or two, use Rider or any kind of IDE, modern IDE, to change that property name all over the place. And message versioning is basically a problem more or less related to microservices and that kind of environment. There is also might be issues with your workflows or your sagas. Say, for example, the third, fourth, or fifth step for some reason did not trigger or send the event to trigger the next step in the workflow. So we'll have to figure out those cases also. I've had those cases in the past where Saga was suddenly stopped for whatever reason. Of course, if you are building all your models inside a single container, you're not going to encounter all those issues because you can use an in-memory message bus, not an external one, and patterns like the outbox pattern and inbox pattern to introduce some resiliency into your system with at least once delivery guarantees, or at most once delivery, once read guarantees. Now, that will solve about 80% of your issues, most likely, but you will still have to decide together with the business, those kind of things. Now, there is also the idea that you should test your system, and all things aside, all sarcasm aside, testing is really important in any kind of system, and testing against those edge cases is really important because having edge cases in a normal run might not be that, you might not encounter them that often, but if you have tests, you might mock some cases where you have edge cases. Now, the types of testing that you can use with a modular monolith is really a lot. You have a lot of ways to test the system, starting with unit tests that you can run against your domain or application, which is inside the service. If we are using a clean architecture setup, you can run unit tests against your domain logic and your application logic. Unit tests will check that behavior really fast and give you a really fast feedback loop and show you if you have any kind of issues. Then the next thing is integration testing, since in my opinion, those are the most beneficial ones in microservices and in modular monoliths, since the issues that appear most often than not are at the level of integration between those components, those modules. And integration testing in .NET is really fun and really easy. I have an entire course, I believe, on YouTube about integration testing, API level integration testing for your system. And you can watch it later and see it for yourself, how easy it is to set up integration tests over there. By the way, integration tests in this setup can be of two types: application level integration tests that run against the public contracts exposed by a model, or API level integration testing that come from outside and are mostly against your routing and your entire system. Both of them are fine. Personally, I prefer API level integration testing since I want to be sure that I don't have any kind of business logic hidden inside the routing layer, since I've had that in the past, happened to me in the past, but that's my personal preference. Now, there are also architecture tests that are really amazing when it comes to modular monoliths. And here is a small disclaimer. Architecture tests will help test the integrity of your system and test against the design decision rules that you have applied. And I've said in the past that you can have different implementation details for your models. You can have different implementation ways. Like, for example, here we have clean architecture. In model B, we can have N tier. In model C, we can have everything coupled together into a single mess. That's all right. But if you want to take out most of architecture tests, you will have to follow some standard when it comes to the internal structure of your architecture. Of your service implementation. So you will profit from the architecture test most. Finally, you can have non-functional tests like stress, load, smoke test. Sorry, smoke is not really non-functional, but hey, spike tests and all that stuff, which can be run from outside your API. And end-to-end tests can also be run against the entire thing easier, because end-to-end tests in a microservice environment are the bane of my existence. You have no idea how hard it is to set things up right there, and how easy, on the contrast, is to set up things inside a single modular monolith. Now, the final challenge for today is basically enforcements. And I mentioned before that you have architecture tests to enforce your design decisions. You also can use the compiler to enforce some of the design decisions, since you can make your classes internal inside the service layer, inside the service class library, sorry. You can make all your classes internal and hide them from external models. But personally, I think the manual approach and the manual enforcement are the ones that bring most of the value. Things like educating the team, explaining to them the benefits of several approaches, explaining them how you want to take them to take decisions in the future is going to bring most of the benefit. You should also conduct regular reviews of their code bases. And here I have a really fun story where a person, where a developer, I'm not going to give any names, decided at some point to introduce some coupling at the level of database via some stored procedures. Obviously, the architecture test didn't pick that up, since it was at the level of the database. So the only way to pick those up is via the code review and regular reviews of the overall architecture, of the overall progress of the team. Also, offering constructive feedbacks for your junior developers, for other developers, is really amazing. And I personally am looking forward to any kind of constructive feedback. Also, finally, there is the make use of decision records or standard documents. Those are something more niche. I mean, there is not much material on the internet about that, at least from what I remember when I was first researching it. There are the architecture decision records templates that you can find on GitHub, and those are really amazing to document your decisions about how the overall system should be structured. And yeah, enforcing them and making the developers write some of the architecture decisions, architecture and design records is going to help you out in the long term, since you're going to have a database of all the decisions and why they were taken in the first place. Now, finally, you will end up with a boring architecture. So if you follow all those rules, you'll have a single repository with a single CI/CD pipeline with a single artifact. The boundaries will be well defined, and each model will be responsible for a specific set of functionalities. Making a change in one model will not impact that much the rest of them, and your teams will be able, your team members will be able to work each on their own tasks without bothering or running into different conflicts with other team members. And obviously, your entire system will be easy to test and easy to deploy. For example, as I said, running end-to-end tests is really easy in Modular Monolith. What else? Well, business will be really pleased with that, since it will hold under control the operational costs and the overhead for managing that system, since it's only one deployable artifact that goes in there. Now, final touch here, we were able to cover only the surface with this talk. I mean, it's an hour already has passed and we've covered only the surface. There is much more content and much more things that you need to study and you need to learn for building a really amazing modular monolith. I gave you only the foundational knowledge and the foundational directions that you should adhere to and you should follow in order to start and get going. And yeah, there are some books over here that might help you out. So the Architect's Elevator and Enterprise Integration Patterns by Gregor Hope is really amazing. I've read both of the books and they helped me a lot at the start. Exploring requirements and quality before design will really help you out to create a framework to explore the non-functional requirements, to explore the functional requirements set before a system. test-driven development is a staple. Fundamentals of software architecture is really also a staple. Building microservices, since you can get inspired a lot from how people are building microservices at scale when it comes to building a modular monolith, since logically they tend to have a similar structure. Writing software, another amazing read over there you have. And also shameless self-promotion. In the left corner, you have a scan me QR code, and I have a YouTube channel. And soon I'm going to be releasing an entire course for .NET related to, well, not only for .NET, for Java and all that stuff, related to modular monoliths, where I cover all of the topics that I've mentioned right here and go even in depth. So you can subscribe to the channel and get notified whenever that one comes out. I'll be really pleased to see you there. And now I have 4 minutes left, so it's time for Q&A session, I believe. Irina, you can